course. Today we'll be speaking English because we have a guest, Tabitha, and Joseph will come later. If he contacts you, feel free to step out and get him, or I can go and get him. Yes, online we have supposedly 2-3 students. Four. Okay. From Rijeka and from Mostar, so welcome. So today we'll be completing the chapter on Ramsey numbers for complete graphs. But before doing that, let me maybe start with a problem, just in case anyone is bored. So we'll be discussing this problem later. It's problem 3.1 in the lecture notes. So it's about lower bounds. So find lower bounds, whatever you can come up with. They don't have to be sharp. For the Ramsey number of path versus complete graph. Then path versus path, and maybe star versus star. So this is k1 t minus 1, k1 t minus 1. So I'll explain this. So this means, finding a lower bound for, say, this means you need to find a red-blue coloring of some complete graph that doesn't contain a red path or a blue clique. And you want as many vertices as possible in your graph. And for the bottom ones, it's the same thing, but this PT is a path, so t vertices. Here, it doesn't really matter if it's t or t plus 1 vertices. And this is a star, so this is a fancy way of writing complete bipartite graph with one vertex on the left and t minus 1 vertices on the right. So it's just a t vertex star. So yeah, if you're bored during class, you can have fun thinking about those problems. Okay, so last time we were dealing with triangle versus cliques, and we proved the following theorem, that the Ramsey number of K3 versus KT, well, actually upper bounds, is at most 8t squared divided by log base 2 of d. So this base 2 is not super important, but we'll be using it today in the calculations. And the important is this logarithmic improvement on the trivial bound. So the trivial bound is t squared. And again, the reason we care about this specifically for triangles is that we also have an almost matching lower bound. And actually, the lower bounds for these, there are several nice arguments. If you want to give a seminar, we can go through various options. So the so-called triangle-free process, or much simpler, there is a very recent paper that uses kind of a randomized product construction to get the best current lower bound on these things. Okay, so today we're doing upper bounds, and we reduce this through the theorem of Aitai, Komlos, and Semeredi, which said that so this is theorem 2.14 AKS. If G is a triangle-free graph, so this means it doesn't contain a copy of K3. And again, if English is a problem, like if there's a specific term that I'm using, please let me know and I'll translate to Croatian. So if G is a triangle-free graph with max degree D, and of course this D should be at least 1, then G contains an independent set on at least n log base 2 of d divided by hd vertices. And again, if you haven't been to the last lecture, you can think about how this statement implies that statement. Okay, there are various proofs of these. I'll use a proof from, and more or less all of them have some surprising where does this come from kind of moment. And I'll use a proof from Alon Spencer book. So we'll consider a uniformly random independent set in this graph G. So G will be a graph as in the hypothesis. And we may assume that D is at least 16. Can someone tell me why we can assume that D is at least 16? This is always all for sufficiently large n. So when D is smaller, let's think what happens when D is smaller than D is smaller than 16, or really the 16 doesn't matter, like any fixed constant. So then this is 4. So then we're looking for an independent set of size at least n over 2D. And why can we always find that? Exactly. So that's just Turan's theorem, or yeah. Here you don't have to use the triangle-free assumption. The whole challenge is this logarithmic improvement, but when D is smaller than 16, this logarithmic improvement doesn't really enter the bound in an important way. Okay, so we assume that D is at least 16, and we consider a uniformly random independent set W in G. And now we define the following not so natural random variable, but I'll try and motivate it. So for a vertex V, we define, for its usual notation, n of V is the set of neighbors of V in G, and xv will be roughly the contributions of neighbors of V to this independent set, but not quite. So we have two cases. It'll be the number of neighbors of V lying in this independent set if V is not in the independent set, and we'll have an extra factor, our summon of D, when V is in this independent set. So for now, you can really think only about this case, and I'll mostly be commenting on this case as we do the proof. This is just an extra factor to make the whole thing work, specifically in the case where in the case when most neighbors of V are contained in this independent set. But we'll see. So we notice that we can express the size. So as usual, the aim is to get a lower bound on the expected size of W, because if we get a lower bound on the expected size of W, then there exists an independent set of this, the desired size, and we'll relate these xv's to the size of the independent set. So if we sum these xv's over the vertices, well, the contribution of this will be the sum over all v's of, so the number of neighbors of v inside this independent set, which we'll reformulate via double counting. Hello. And for the other term, it's even easier. So this one, for each vertex in W, we get an extra sum of D. So this contributes precisely W times D. Okay. So Joseph, welcome. Don't worry about being late. I'm glad you made it. So we're basically proving this statement. Okay. And the statement is, if we have a triangle-free graph with given max degree, then we can find a large independent set. And the point is that because you're triangle-free, we'll get this extra log improvement. That's very briefly. So we're working in this triangle-free graph, and we have chosen a random independent set W, and we're trying to calculate the expected set size of W. And now this is the sum of xv. I'll just write v in big V, which means the vertices of G. Okay, so how can we reformulate this by double counting? Well, we have this W, and for each V, we count how many neighbors does it have in W. But that's the same as counting from the perspective of W vertices. So we're counting for each W how many neighbors it has. And here notice that it doesn't matter. So we can, if you really want to convince yourselves that this works, regardless of whether your vertex is in this set W, you can consider two cases. So, and this is you. So if this edge UV is entirely in W, then it contributes to this sum twice, both for U and V. And in the other case, if this vertex U is inside W, but its neighbor V is not in W, then it contributes only once. So, yeah?
Question. W is an independent set, there's no edges in W.
Yeah. Yeah, actually that's correct. Sorry. W is anyway an independent set, so yeah. So yeah, we're only considering the edges going out. So really this is just counting the edges between W and its complement in two different ways. Yeah. Okay. So the size of the neighborhood of U plus this extra WD. And this is now at most because of our bound on the max degree. So we have W terms, and each of them have size at most D. So this whole thing is at most 2 WD. So this means that specifically, so deterministically, the size of W, so this is for every independent set W, the size of W will be at least this sum divided by 2D. But specifically then, if we take expectations and use linearity of expectation, we'll get that 1 over 2D, the sum over all these vertices of the expected size of the neighborhood is at most the expected size of W. So again, this inequality holds for all W, but where taking expectations and taking a random W helps is that we will have an upper bound on the expectation of this for every single vertex V. So before writing that, let me just comment on this extra factor of D. Notice that here we took a factor of D because that way this, well, one reason we took this summed to be D is that this extra term does not contribute significantly to this sum of xv's. So when we want to now lower bound the size of W, then up to a constant, this term doesn't change anything. If I took something larger here, say, I don't know, D squared, then it would mess up our lower bound that we have in W. Okay, so we claim that the expected value of xv is at least log 2d divided by 4 for every v. And this will then imply our desired bound, because then we'll have that the expected size of W is at least, we have here n summands, and each of them is at least this. So altogether we'll get a bound of n log 2d divided by 8d, which is exactly what we're aiming for. Okay, so we reduced the problem to this calculation, and now the way we'll bound this expectation is also somewhat unexpected. So we'll first, remember we fix a vertex v and we want to analyze this. So we'll consider first the non-neighborhood of v. So we'll define a set TV to be all the vertices minus v and its neighbors. And we'll expose W intersect TV first. So this means that I look at this set, if this is V, these are its neighbors, these are its non-neighbors. It means that I will expose all the W vertices in here, so I will tell you exactly in this set TV which vertices are in W and which ones aren't. So we're going to condition on that and then bound everything else conditional on that set. In plain language, that means that whatever set here plays the role of W intersect TV, we will have this lower bound regardless of that intersection. Okay. So okay, so let S subset of TV be, well, an independent set, and we'll show that conditional on W intersect TV being exactly this S, the expected value of xv is still at least what we claim. Okay. And then formally, I won't write it, but formally the way you get rid of this conditioning is you sum over all the possibilities for this S times the probability that this equals precisely S, and you get a lower bound on the expected value of xv. Okay, this I hope you copied if you're doing the problems. Okay. So now, to analyze this, so the important observation is now that we're interested in the rest, so how does W intersect with the neighbors of V? And now the important thing is that these are an independent set because our graph is triangle free. So this means that W can be any subset, well, the rest of W can be any subset of this, what we'll call U. And it will be, or we won't call it U, and it will be any subset of that with equal probability. And then we also have the case when V is included in W, because then none of these can be included. So we have two cases, either V is included, then we're done, or V is not included, and then we have subset of its neighbors. But of course, some subsets of it, I cheated slightly, some subset of its neighbors that don't have, that are not already forbidden. So if someone here already has a neighbor in W, then it's automatically forbidden. So we'll call U to be the candidate set, so the vertices that are not forbidden yet. So U is the set of I don't know, X in the neighborhood of V, which are not adjacent or incident to W intersects TV already, or S rather. So we've conditioned on this thing being S. That's fine. So again, there's a slight subtlety there that again we've exposed S, but that is independent of what happens inside the neighborhood of V. And we let little u to be the size of big U, and now there are, so this U is an independent set. It's important. And hence, there are 2 to the little u plus 1 options for how this W intersects V and its neighbors, or more specifically, V and U. And again, 2 to the U stands for each subset of U, and 1 for the option that V is included. And then, depending on those two cases, we have the following bound. So we have the expected value of xv conditional on W intersects TV is S. So for the first case, we actually split into two cases. So the probability that this thing happens, so that it's one of the subsets of U, is 2 to the U times 2 to U plus 1. And now the important thing to understand is that if I tell you that this W fragment is a subset of U, then these are really by like independent coin flips. From each U, for each U vertex of U, I flip a coin and tell you whether it is in W or it isn't. because that's an alternative way of generating a uniformly random subset. So that means that now this term, or this term, will be in expectation u over 2. So once again, if the question I'm asking is, if I condition on v, so this expresses the conditioning, if I condition on v not being in my independent set, how many of its neighbors do I expect to be in the independent set? And that expectation is precisely this. And then on the other hand, if I have the case that v is in W, then I need this extra term, because in that case none of its neighbors can be in W, but I have this D, and that'll save me. Okay. So then here we have some function of u and of d, and we claim that for every u, this function is sufficiently large. So we claim that this is at least log 2d over 4 for every u. And that then completes the proof. But I'll explain a bit more, so I won't do the calculation. I think it helps more if I explain the intuition than if I do this calculation. So again, the kind of dominant, at least by probability, the dominant case is when W does not contain V, and it contains some of its neighbors. And notice that for this, for this term, this you can consider to be essentially 1. So as long as this u is of at least logarithmic size, this term is sufficiently large. So you can think of this case as covering all the vertices V of sufficiently high degree, let's say. And then the other case covers morally vertices V of low degree, because those vertices of low degree are more likely to be in our independent set, and they kind of, it helps us to include them in the independent set. And however, they won't have many neighbors in the independent set, so that's why we added this extra summand of D. And now, how do we optimize this function? Well, you can always just do your calculus, find the minimum in terms of u. The minimum will happen roughly when u is log d over d. But usually, really, the heuristic way to do it, or in this case even rigorous, is to consider when these terms are roughly of equal size. This is kind of general when you have these two competing terms. The minimum or maximum usually happens when these two terms are of equal size. And here, based on what I just said, you can actually just split it into cases. So if you consider the case when u is at least logarithmic in d, then this term is fine. And then you consider the case when u is smaller than logarithmic in d, but then this is at most, I don't know, 1 over square root d, say, and then you get this term to be sufficiently large. And then again, maybe a natural question would be, I chose this function, so why wouldn't I choose something huge here to help me get a better minimum? But then the problem is that would fall apart here. Okay, any questions about that proof? Okay. So that is the Ajtai-Komlov-Semeredi proof, and again, because it's it resulted in extremal combinatorics, it has a number of other applications. One thing you can do, which is also in the problems, is to use it to get a better upper bound on other Ramsey numbers. So remember, the standard proof of Ramsey numbers goes by induction. So if you just plug in the improvement that used to be here, So if you plug in that improvement into the the higher values of Ramsey numbers, you do get an improvement. One very interesting recent application of this kind of result is in sphere packing. So I stole that from the lecture notes of Yuval Widgerson, which you are welcome to look up. So basically, recently there was a lower bound on sphere packing density, and so let me just say, do a little digression on that problem. So interlude or application, sphere packings in R to the D. So you're interested in the densest possible sphere packing in R to the D, and a sphere packing is just a collection of disjoint unit spheres. You try and pack as many of them in R to the D, or rather cover the densest possible set of points. So a 2D sphere packing may look something like this. And maybe again a question for you while we discuss this is, what is the densest possible sphere packing in 2 dimensions, and in 3 dimensions if you want. So in general, we define very informally theta of D to be the density of the densest sphere packing in RD. So that's informally. Formally, what you need to do is, first of all, for a given packing, something like this, you need to be able to compute the density. And the way you do that is really by taking limits. So you take a large box of this packing, you compute the volume, and then you take the lim sup, I guess, of those volumes. So, okay, and then for this theta of D, you want the maximum over all these different options for the packing. And this thing is actually known in dimensions, well, 1, 2, 3, 8, and 24. So dimension 2 was resolved by Thue in the 19th century. Dimension 3 was conjectured by Kepler in the 17th century, but it was proven by Hales, and Widgerson says it's a long, heavily computer-assisted proof, and but it was formalized by a proof assistant. And the reason that these two are resolved is the lower bounds. So here both is difficult, obviously, upper and lower bounds, but even to construct lower bounds you need something very structured like this. So you need some kind of lattice that will, and specifically a lattice in R to the 8 or a lattice in R to the 24th, which will allow you to have a nice sphere packing. And then, of course, you need to prove that that lattice is optimal. So for dimension 8, this was done by Wiazowska, and for 24 by her, Wiazowska, and Quarters, Kohn, Kumar, Miller, Radchenko. And she won a Fields Medal for that work, amongst other things. So, yeah, maybe to answer the question, what is the optimal packing for dimensions 2 and 3? Just kind of intuitively. Almost. It's the dual. It's the triangle. Well, it's depending on how you consider it, but yeah, it's the dual, so it's a triangular lattice like this. But I guess these form the hexagonal lattice, the touching points. So you can also say that it is the hexagonal lattice. And for 3, I guess it's some kind of tetrahedral lattice, so it's like the way oranges are stored in a supermarket. Okay, so for general D, we only have asymptotic bounds, and they're nowhere near optimal. We don't even know the correct exponent, meaning that so the current and very recent bound is best lower bound for general D. D is theta of D is at least, let's say, D ln D over 2 to the D plus 2. So that was done by Campos, Jensen, Michelin, and Sahasrabudhe. Campos and Sahasrabudhe were also in this group on diagonal Ramsey numbers. So this, we don't even know the exponent. So this is a significant mathematical result, but really this exponent may not be correct, and that's a classical bound due to Rogers. And then someone else improved it to this type of bound, and therefore for years there are many improvements for the constant. And then this group added an extra log term, which again doesn't sound like too much, but it's an important problem on mathematics worked on by many people. And this log D might remind you of this logarithm, and they are kind of related. So there is a part of the proof, allegedly, so that's only a small part, where they use this type of bound. So what they do is they construct a graph, and they start by constructing a randomized graph. But this is not just uniformly random, but it has to be some specific clever methods to get a graph with specific properties, or rather a set of points, like a random set of points. And then in the set of points, they connect 2 of them exactly if they're at distance less than 2, because that's when their spheres intersect. So what you really need is an independent set of that graph. And then what they do is they design their graph in a way that it doesn't have too many triangles. So it does have some triangles, but it's a small number. And then from the small number of triangles in this graph, they get an independent set of this size, which then in their world corresponds to sphere packing. So again, another paper that you're welcome to look at if you're interested. And another kind of general lesson from that paper is that often it's kind of about the right combination of geometry and combinatorics. So of course geometry matters, but then at some point in the problem you want to like strip down, reduce the structure to just combinatorics and see what the tools of, say, Ramsey theory can give you. Okay. And that is all I'm going to say about Ramsey numbers for complete graphs. So we're going to move on to the next chapter about Ramsey numbers for general graphs. But before that, I'll just restate the exercise that I had, and then maybe do you want 5 minutes to just introduce yourselves and say what you're doing? Yeah. Okay. So again, R of PT and KS. So we wanted lower bounds for these Ramsey numbers. So you're welcome to think about that during the break, or you're welcome to interact with our guests, especially if you want to get invited to India. No guarantees. So yeah, today we have Tabitha and Joseph visiting. So yeah, thanks for coming, and maybe if you want to have a word.
Yeah.
Okay. Right.
Good morning. My name is Tabitha, and I've been teaching on and off for the last 30 years. I began teaching undergraduate students right after I finished masters. So my first job, I was just 22 years old when I began teaching. And one of the first few courses that I taught was abstract algebra, and I felt very satisfied when I was teaching that course. So then I realized that this is what gives me joy. So in between I had some long breaks, maternity breaks I had taken, and then I came back to, I taught in schools as well, but off late I've been teaching in a university called Christ University, and it's 11 years with the university. So I teach undergraduate students and postgraduate students as well. Again, I teach courses like discrete mathematics, abstract algebra, and graph theory. So graph theory, my response, the response I get from students is very interesting. Either they completely fall in love with the course, or they detest it, they don't like it at all. Especially those who learn abstract algebra well, somehow I can always guarantee that they will like a course like graph theory. But somebody who has difficulty with thinking abstractly really struggle at this course. And I liked the way she introduced some problems and then theory as well. So when I teach these undergraduate students, some of them get very excited with the problems, but the theory is, the theorem proof is slightly difficult for them to handle, and it's always challenging. And we use books like Chartrand and Introductory Graph Theory by Chartrand and Zhang, and then we use at master's level textbook by D.B. West. So these are the books, probably I don't know what books you are introduced to, but in masters what we do is, in the very first semester when we introduce graph theory, they take a call whether they want to specialize in graph theory or specialize in some other discipline of mathematics. So maybe first semester or second semester, by then they take a decision. So those who want to pursue research in graph theory, stick on to graph theory. They do other courses as well, but they will do extra courses in graph theory. And same is the case with other disciplines. If they've chosen fluid mechanics, they pursue fluid mechanics extra courses in the second year. So I love the class. I love the way she introduced the topic and the theorem as well, and the way you're responding to it. And I wish you all the very best. And in future, if you ever want to visit India, please come to our university. You can interact with the master students of our university as well. Some of them go on to do PhD in graph theory, and they go to other universities or sometimes stay back in our universities as well. So all the best to all of you. Thank you for having me here.
Thank you.